Okay, we are back again looking at some applications of integration, and we're going to take another look at particle motion. We can determine the values for positions and rates of change using definite integrals in problems involving rectilinear motion. What does that mean? Straight line motion. Particle motion problems deal with motion along a straight line, both horizontal and vertical. And now it's possible for us to work in two directions. In other words, the last time we looked at particle motion together, we would take only derivatives. We'd start maybe with, the position function, take the derivative to the velocity function, and take the derivative again to the acceleration function. But now, with integration, we can go the other direction. So, for an example, if an object is traveling in a straight line, then its velocity can be expressed as the integral of acceleration. So, three types of questions you might be asked when dealing with this kind of thing is the displacement, the total distance traveled, or the final position. So, it's important to figure out, what's the difference between those three things? Well, let's say we have a particle moving in a straight line right and left. This is a velocity function right here. And whenever the velocity is positive, the particle is moving to the right. Whenever the velocity is negative, the particle is moving to the left. So the displacement just kind of compares where it starts to where it ends. So for this particular particle, our displacement would be area 1 minus area 2, because that's negative, and then plus area 3 again. Now the total distance traveled, we don't care if we're going left or right, so anything under the x-axis actually counts as positive distance. So it would be area 1 plus area 2 plus area 3. Now final position is just, wherever you started plus the displacement. Example 1, given the velocity graph of a particle p from time 0 to 10 and s of 0 equals 4. We have an initial condition there. We're going to find the displacement, the total distance traveled, and the final position of the particle. So first of all, the displacement. We've got a positive 18 and a negative 12. So that's 18 minus 12 is 6. But to write that in calculus terms, we've got the definite integral from 0 to 10 of our velocity is 6. Now the total distance traveled, everything counts as positive. So this would be 18 plus 12, which equals 30. And to write that in calculus terms, we need to put the absolute value there on our velocity. And for the final position, we just take where we started, which is our initial condition here. We started at 4. And we're going to add the displacement to that. So 4 plus 6 equals 10. Okay, now this one's going to take a second to break down. I'm going to read through the paragraph, and as I do, we're going to work through this graph here at the bottom right. A particle moves along the x-axis so that its velocity at time t, between 0 and 15, is given by a differentiable function v, whose graph is shown below. Okay, so let's just pause and remember, this is a velocity graph, and it's important to make that distinction. At time t equals 0, the particle is at s equals 4. So what do we have so far? We know that the antiderivative of velocity is position. We also know that the derivative of velocity is acceleration. We also know that we have a starting position of 4. And if you're taking the AP exam, you need to write all of these down. You need to establish the relationship between velocity, position, and acceleration. And then you can use these terms as you need to as justification or explanation. Okay, let's keep reading. Where are we? The velocity is 0 at times t equals 3, t equals 9, and t equals 13. And because the graph is going through the x-axis at those times, crosses through the x-axis, then that's when we know our particle turns around. The graph has horizontal tangents at t equals 6 and t equals 11, and the areas of the region bounded by the t-axis and the graph are as follows: 6, 9, 3, and 2. Lots going on there. And again, just a reminder, we have a starting position of 4. That's going to come in handy. That's also nice just to mark where we're ending. We're ending at 15 there. Part A. So for time between 0 and 15, find the time and position of the particle when the particle is farthest to the right and justify your answer. Well, we have a starting position of 4, and it's going to be farthest to the right, well, at the end of a positive region. So let's see, S of 3 is our starting position plus the area. 4 plus 6, which is 10. Then it goes backwards for a little bit, and then it goes forwards again. So at S of 13, we have our starting position plus 6 minus 9, and then plus 3 again, which is 4, which means the particle is furthest to the right at S of 3. For how many values of t between 0 and 15 is the particle at x equals 4? And explain your reasoning. Well, let's see what we have. We know our starting point is 4, so that's 1. Now let's see what happens at all of these zeros and the end point. S of 3 is 10. S of 9 is 1. S of 13 is 4, and S of 15 is 2. Okay, so by the intermediate value theorem, somewhere between S of 3 and S of 9, there's a 4. Because there's a 4 tucked in here between 1 and 10. And then S of 13 is 4, so we've got the starting point somewhere in the middle, and then S of 13. So there's going to be 3 values when the particle is at x equals 4. On what intervals is the speed of the particle increasing? Now recall, speed is increasing where the signs of velocity and acceleration are the same. So whenever, let's go positive first. Whenever velocity and acceleration are both positive, that's just this little guy right here. Velocity is above the x-axis, and there's a positive slope. That's acceleration. So just between 9 and 11. But we can also look at the negative. So when velocity is negative and it has a negative slope, that's another spot there and, whoops, over here too. So between 3 and 6 and 13 and 15. On what intervals, if any, is the acceleration of the particle positive? So positive acceleration is going to be a positive slope on the velocity graph. So where's that? That would be, let's see, right here. It's the positive slope on the velocity graph. And I think that's it, between 6 and 11. Okay, let's see, new example. An object moves in a straight line with a velocity of the square root of 3t minus 2 meters per second, where t is time in seconds. At t equals 5, the object's distance from the starting point was 12 meters in the positive direction. So we have kind of an initial condition here. Write an integral expression that will compute the object's position at t equals 10 seconds. So if we know that at time t equals 5, we were at 12, we'll take that 12 and then just add the next 5 seconds to it. Okay, so that's our integral expression. Part B says find the actual position of the object at 10 seconds. So just pop that into your calculator. We've got about 34.5 meters. Example 4. A particle is moving along the x-axis with a velocity of negative t squared plus 7t minus 10, measured in meters per second after t seconds, with an initial position of s of 0 equals negative 3. I always like to highlight my initial positions so that I don't forget about them. Part A says determine the displacement of the particle on the time interval from 1 to 7. The displacement. Okay, that's just going to be the definite integral from 1 to 7 of our velocity. So we can go ahead and work that out. Take the antiderivative of each of those little pieces. We've got negative 1/3 t cubed plus 7/2 t squared minus 10t. And we'll evaluate that from 1 to 7. So we got f of b, f of 7 minus f of a, or f of 1. And that all works out to negative 6. So we have a displacement of negative 6. But what's the total distance traveled by the particle? Well, that's interesting if you have to do it by hand. So in order to do this by hand, we're going to have to figure out where the particle changes positions or turns around. So in order to do that, we're going to have to find the zeros of the velocity function. So that's going to be at t equals 5 and t equals 2, which means we're going to have, well, a couple different integrals that we're going to have to figure out. We'll have to go from 1 to 2 first, then add to that 2 to 5, then add to that 5 to 7, and in each of these integrals, we're taking the absolute value because the distance is always going to be positive. So that would turn out to 15 meters. Just a note of caution, when finding distance, always check to see if the zeros of velocity are inside the range. So find the zeros and then put together your little pieces. But if you have a calculator on hand, or if a calculator is allowed on a particular problem, this you can actually just plug straight into the calculator as an absolute value function, and it'll do all the heavy lifting for you. Suppose you're driving in traffic behind a large, slow bus at 66 feet per second, which is about 45 miles an hour. When you finally get a chance to pass, you step on the accelerator, giving the car an acceleration of 4 over the square root of 2, where a is measured in feet per second, and t is measured in seconds. How fast are you going 16 seconds later when you've passed the bus? In order to figure out how fast you're going, we're going to need a velocity function. And velocity is the antiderivative of acceleration. So we'll take the antiderivative of 4 over the square root of t, and that's 8 times the square root of t plus c. Don't forget that constant of integration. So we do have an initial condition here that we can use to solve for c, and that's at time 0, we're going 66 feet per second. So we know that c is 66. So here we have our velocity function of this whole situation. And to know how fast you're going, 16 seconds later, we plug in 16 to that, and you'd be going 98 feet per second. Not bad. How far did you travel? Okay, so that's total distance. That'll be the absolute value of velocity from 0 to 16 seconds. Thankfully, this is a calculator question. So you will have gone 1,397.33333 feet. Now, what's your average velocity for that 16-second interval? Well, we'll take our total distance traveled divided by 16, which would give us 87.333 feet per second. And now you're frustrated with calculus, perhaps, and you go to a window 48 feet above the ground and drop your book. Question is, how long will it take for your book to reach the ground? There is not a lot of information. The only thing we have is 48 feet above the ground. So let's see, what do we know? Given. If you drop the book, you have initial velocity of 0. We also know that acceleration is -32. How do I know that? Because on Earth, we have a gravitational constant of -32 feet per second squared. All right, that'll come in handy. We also have a starting position of 48. All right, let's figure out a velocity function. So in order to find velocity, we're going to have to take the antiderivative of acceleration. So we get -32t plus c. We have an initial condition of 0, 0. So we know that c is 0 and our velocity function is -32t. From there, we can find our position function. So we'll take the antiderivative of -32t. We get -16t squared plus c. We have an initial condition of 0.48 that we can plug in here to find c, and c is going to be 48. So we now have a velocity function and a position function. Now, what were we even asked at the beginning? How long will it take for your book to reach the ground? Okay, so that's when position equals 0. That's the ground. So we can solve for 0 with that position function, and we get t equals square root of 3 seconds. That's pretty quick, I think. What is the velocity of the book at the instant it reaches the ground? Well, we can take that cube root of 3 and just plug it right back into our velocity function. About -55.426 feet per second. Okay, we have another bus situation. A school bus accelerates as it leaves one stop, but then it decelerates as it comes to another stop. So the chart below measures the velocity v given in miles per hour between each stop. Find the distance the bus travels between every interval. Now this is a table, so we don't have a ton of information. The best we can do is kind of estimate. And do you remember how we can estimate area using a table of velocities? We're going to use the trapezoidal sum on this one. So the area of a trapezoid is 1/2 the height times the two bases added together, or the average of the bases times the height. So for example, this first interval here, okay, would be 1/2 times the height of the function. So we've gone 5 out of 60. So that's 5/60ths. And then let's see, the two bases are 0 and 18. So that would be about 0.75. So our first distance, well, we haven't gone anywhere. Then our second distance hack would be 0.75. And then you'd repeat this process for each of these intervals. Okay, so you can stop the video and do that on your own, or you can trust my math, which is a scary proposition. Part B says find the total distance the bus traveled in 60 minutes. So of course we just add all these up and you get about 17.257 miles. So it's fun now that we can go both ways. We can go from position down to acceleration, and if we want, back to position again with integration. Thanks for being here.